Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Cloud seminar. Today, we have Lyonell Boulton from Heriot-Watt University, who will tell us about spectral analysis of Dirac operators with a purely imaginary dislocation. Lyonell, the floor is yours.
Thank you. Thanks, Jan, and thank you to Alexander for the invitation. And well, what I'd like to report today is joint work with Nguyen and David Krejĉiř, both from the Czech Technical University in Prague. And well, To is perhaps the main engine behind this. His stamina has been crucial for us to finish the project, really. So the context, the following. We know a lot about non-self-adjoint operators. I mean, this is work that has been accumulated over the last 30 years, seminal results by Davis and others have been developed to create generality and depth. But we know very little about non-self-adjoint Dirac operators. Systems are different from scalar models. When we introduce a dislocation into a model, weird things can happen. I'd like to combine in this talk, in these mathematical results I want to present to you, these two ideas. Yeah? So let's combine these two ideas. And this is not a survey talk. I want to show you specific ideas. I want to show you results and proofs. But the context is a paper that Nguyen, Laptep, and Krejĉiṟ published in the Annals of Henri Poincaré in 2014 about Dirac operators, one-dimensional Dirac non-self-adjoint perturbations of Dirac operators. And their results are about what happens if a potential has decay such that you can recover the properties of the original non-self-adjoint model. And counterpart to that is the work of Henri and Krejĉiř, and that's a second paper I would use for what I want to do. And in that paper, they consider Schrödinger's operator perturbed with dislocation and potential that has discontinuity at the origin and a jump of purely imaginary. And then what happens if I take that as the unperturbed model and consider the problem of how the spectrum changes whenever I add a potential that decays at infinity, a long range potential, for example. Yeah. So these are my base work I would like to combine. And the results I want to present are about the following unperturbed operator and perturbations of that. So consider that I have a parameter m, non-negative, that's the mass, and suppose I have the standard one-dimensional Dirac operator perturbed by a jump at 0 with sign. Okay, so the function isgn stands for -1 whenever the variable is negative and +1 whenever the variable is possible. Identity matrix. So suppose I consider this operator as a, and let me call it just for the sake of this talk, dislocated Dirac operator. This is my base operator. By the Dirac part, what I mean is a standard one-dimensional Dirac operator. Sigma in the screen are the Pauli matrix, sigma 2 and sigma 3. And in matrix forms, I'll regard the operator like that. It's a close in the subgroup space H1 on L2 of two components. What happened?
Excuse me, Lyonell.
Yeah.
What is the sign for it's complex valued, right? So it's not just positive or negative.
The variable is real. The variable is x. So SGN stands for -1 if x is negative or +1 if x is positive, and I'm multiplying by an I.
Yes, thank you, sorry.
Yeah. So essentially my potential is -I whenever x is negative plus I whenever x is positive. Yeah. Okay, so I consider L, suppose I have a way of, I have a closed realization of L plus a potential B, an L1 potential. I'll say more about that later on. Potential could be just any Hermitian matrix, L1. What is the spectrum of that? This is what I'd like to report. So what's the structure of the spectrum of this model? What's the structure of the pseudospectrum of this model? Spec epsilon, for epsilon greater than 0. So that's my talk essentially. I like to talk about these operators, and I'd like to start with the numerical range on the case v equal to 0. So I'll call this the instability band, and it's nothing else but the field at which the energies of Lm only v equal to 0 live. Yeah. So I claim that the numerical range is a band around the real axis of width 2. Let me prove that. And so by numerical range, the terminology refers to the field of value. Sometimes this is the old terminology. What we mean is just all quantities of the energy associated to Lm for normalized wave functions, norm 1. Yeah. When I write the inner product, the brackets refer to the inner product of operator ff. Suppose that my wave function has two components in H1, then so that expression reduces to a real part. I'm showing that, moving the arrow in the numerator in the screen just now on the top, and then the imaginary part is just that. So what is this? I have a real part that depends independently of the components of my vector, a term that is dominated by that, essentially, and then a term that involves the support of f. So I have enough freedom here to say that this, which is bounded in modulus by 1, is giving me all possible imaginary parts of the numbers here. And this is the real part. As it turns, we can prove that it's unbounded. So you see, we can freely choose the entries, we can freely choose the support. So we can use the fact that the numerical range is convex. This is a convex set. For if I move all f in H1 with norm 1, that's it. That's me. So that region is, let me show you a cartoon picture if you want, is where all the action is happening, spectrally speaking, about Lm. So essentially, we will see results involving what's happening inside the band, and it's not that interesting what happened outside the band, but we'll see why that is the case. So that's the numerical range of my operator. And so the rest of the talk is in two parts. And the first part is about no potential, case B equal to 0. So there is a natural distinction between the case of mass 0, m equals 0, and m greater than 0 in the structure of Lm. I'll explain that why just now, and then we'll see that the results naturally splits in these two cases. Suppose that m is greater than 0 first. Well, we can prove that the spectrum is purely essential for the 5 different types of essential spectrum, and it's the following. It's comprising 4 segments parallel to the axis at height imaginary equals to 1 and starting at real part in modulus greater than or equal to m. Yeah, so the segments m real part plus I minus I, and then minus m real part going all the way to minus infinity. I'll show you why this result holds. I mean, I'll show you part of the proof of this. But for the messages for m greater than 0, the spectrum is purely essential, and it doesn't matter which definition for essential spectrum, which class of essential spectrum you put, it happens to be the same set. If On the other hand, we consider m equals to 0, and I'm drawing the picture on the right side of the screen. Now, what we have is that the instability band fills in. Yeah. So as it turns, if I wanted to mimic this result for m equals 0, I only have the boundaries, the segments at height plus minus I. But in turns, what we have is the following for the spectrum of L0. All of the EJ essential spectra up to 4, j equal 4, are the segments that mimics the case of positive mass. But then E5 is the full band, right? So this is a natural distinction with this case. There is an explanation. I'll tell you why in the next slides. And this is not that uncommon in a sense. The E5 spectrum is the one that splits normally in a model that depend on a parameter. Okay, so let me show you the proof of these results. I mean, a sketch proof, but let me show you why these results about the model, the operator LM. Spectrum included in either of these. Yeah, see, this is the case m equals 0 in cartoon picture, or the case m greater than 0, and the case m equal to 0. Yeah. So how do we prove these results? And so let me put it like this before I start. It's sweat and tears. So essentially what we do is the following. We write explicitly the kernel associated to the resolvent of Lm minus z. We compute explicitly for any z in suitable regions. And what we do is regions, the complement of either of these two, the matrix norm. So the kernel is a 2x2 matrix depending on z. It's a complicated expression. It's a horrible, I should say. And we compute explicitly the matrix norm. Essentially, the kernel looks like this. Yeah. So we divide the plane, so two real components, x and y, plane x, y, into the 6 regions that have a common expression for the kernel. Yeah. So if you've done these calculations before, this is the natural split of the regions in which there are the singularities. The boundaries of this region have the singularities of my kernel. And so just this is just to show you the structure of the kernel. It's 10 matrices, n1 through to n10, depending on z, 2x2 matrices. I'm not showing in the screen the structure of these matrices, but we need to compute. So it's the entries of these matrices and have rational expressions in terms of z and the other variables. And then exponentials. I mean, these are the important bit. It's combinations depending on the regions of exponential with plus or minus the variables. Yeah. What happened is that for the parameter z, that's the spectral parameter outside, either for m greater than 0, this picture, or for m equal to 0, this picture, we have, for example, this mu, which is the coupling constant for the exponential, is positive. Yeah. So what we have, it's negative. So what we have is decay at infinity. So let me see if the sign is right. So y less than x. No, what I meant to say is that mu is positive outside this region. So what we do is, for the proof, we pick a z outside. We have the integral expression for the kernel, and we use the Schur test to prove that defines a bounded operator in L2. Then we prove that this integral kernel matches L minus z to the -1, and that's us. Yeah. So the complement of this would be in the complement of that. What about the proof of the complementary inclusion? Yeah. So what about points on this segment? Why is it that they are on the spectrum? And the proof uses, well, construction of the singular Weil sequences. So, this mimics the natural calculations that you do in the self-adjoint regime. Yeah. So we construct the singular Weil sequences, which look like the following. It's a product of three terms, constant, 1 over Cn, cutoff, and an eigenfunction as follows. I pick Z real plus I on the corresponding segments. I'm considering the case of positive mass now. My constant is one that normalized to 1 my pseudo mode. So singular White sequences, I'll call them pseudo modes as well. I consider the eigenfunction corresponding to the equation for just the Dirac operator on the real value tau. And this is this eigenfunction here. Yes, it's of exponential type. This quantity here, remember, tau square is greater than m squared. So this is an oscillatory term. The cutoff makes sure that this is L2. The constant makes sure that this is of norm 1. This is weakly convergent to 0 because my cutoff takes the support to plus or minus infinity. I'm picking the sign here. And then as it turns, when I evaluate operator minus z at that is of the form square root of constant over n. So it goes to 0 as n goes to infinity, as the support of the cutoff goes to infinity. So it's just a calculation, but as it turns, these are the right singular White sequence to ensure that my E2 pseudospectrum, sorry, my E2 spectrum is these segments, yeah. So the E2 spectrum refers to the existence of singular Weil sequences. So we know that this set is in the E2 essential spectrum of my operator. But we have symmetries, and I'm showing, and I'm reading at the bottom of the slide. We have symmetries such as, for example, transposition. If I take the entries of my vector of two components and transpose, then the operator L intertwines via the transposition with L star. And that means that all of the E1 up to E4 types of essential spectrum are the same. Yeah, we know that E2 is in here, and then the same happens for the E1 up to E4. And what about E5? Well, this is an essential spectrum which has a complement. The complement of E1 in particular is connected. So the E5 will coincide with that. I mean, if you remember the E5 spectrum, essential spectrum is the one is that is either E1 or the points in the resolvent set that do not intersect with the components of the complement of E1. Yeah. So that's that. My right-hand side is in the all of the spectra LM, and they correspond to purely essential spectrum. What about the case m equals 0? Yeah, so why do I have a distinction between the E1 through to E4 and then the E5? Well, in that case, the same argument works. I repeat the proof, and what happens is that the segments are indeed in the EJ from 1 to 4. I prove by hand that the kernel, whenever Z is inside the band, has dimension 1. The joint operator has the same kernel dimension. I prove that the range of L0 minus Z is close for any Z inside the stability band. So then what I have is that the E3 spectrum is exactly the segment. E3 is the one that corresponds to the not being Fredholm condition, yeah? And we are proving that for any Z inside, the operator is Fredholm. And then all of the other, because of the symmetries that we have, all of the other J from 1 through to 4 also are just a segment. But for E5, I have 3 connected components, and no eigenvalues inside the interior of the instability band is isolated. So E5 happens to be just a closed band. Yeah. Outside there is nothing because the numerical range does not have. So at the outside we know that it's in the resolvent already because the numerical range is just the band. So that's the structure of the spectrum for my operator without the potential. Okay, this is the case 0, and the previous slide corresponded to the case greater than 0. Now, the pseudospectrum. Yeah, so what is the pseudospectrum of the no mass case? So let me carry on with the case mass equal to 0. Well, in that case, I have a spectrum, which is the band. I have a numerical range, which is the band. Outside, then the resolvent norm decays to distances linear to the boundary. So my pseudospectrum is just the band corresponding to imaginary 1 plus epsilon. Epsilon is the pseudospectral parameter here. It's a trivial pseudospectrum. Yeah, in a sense, in terms of the pseudospectrum, the case L0 is trivial. However, there is an interesting question that we don't know how to answer. For example, so the question is the following. Is L0 similar to a normal operator? So we know that if an operator is normal, then the pseudospectrum is the neighborhood, the epsilon neighborhood of the spectrum. You know, if an operator is similar to normal by an unitary, then the same is true. If it is similar to normal by a non-unitary transformation, well, the pseudospectrum is trivial by multiplying by a certain parameter here, the instability index corresponding to the similarity transformation. The condition number is called sometimes. So we have an operator whose pseudospectrum is trivial, but we don't know, and it's not that easy to prove that whether this operator is similar to normal or not. Yeah. So that's a question about this model L0. Now, for positive mass, the pseudospectrum is not trivial. Yeah. So let me tell you what we know about that. And so I have the following regions depending on a parameter alpha. So my parameter alpha is fixed between 0 and 1, let's say a half. Yeah. And I consider regions lambda plus and lambda minus. One is an inclusion, the other one is an exclusion of the pseudospectrum. I'm showing the theorem at the bottom of the slide. And I'll show pictures of the region in the next slide. This is the algebraic definition, okay? Imaginary part is just the epsilon neighborhood of the instability band, and then the real part is kind of, I control the square of the real part by 1 over epsilon, essentially. This is the result. What we know about the pseudospectrum is that there is a constant independent of epsilon, such that if I view what happened for the pseudospectrum in the channels of a instability region away from the axis imaginary, real part of Z greater than M, then we have an inclusion. So we know that certainly the lambda minus region is in the pseudospectrum, and we have an exclusion. Then we know for certain that the lambda plus region contains the pseudospectrum. Okay? Let me show you pictures of that for values of the parameter. Yeah? Same theorem at the bottom, and at the top we have, for example, mass 1 and alpha 0.1. Alpha close to 0 is ideal because what's happening is that these two regions are getting closer to one another. We really are getting sharp estimates for the pseudospectrum away from the imaginary axis. So we have two graphs in the screen, and we have two regions being depicted. The lambda minus is the orange kind of region, and the blue that you see is the difference between the lambda minus and the lambda plus. The lambda plus is covered by part of the lambda minus. And what we are saying in this theorem is that the boundary of the pseudospectrum lives in between these two curves. As alpha goes to 0, they get closer and closer. So what we are saying is that there exists a constant such that these two enclose and exclose the pseudospectrum. Namely, the boundary of the pseudospectrum is in between these two. We suspect that the boundary of the pseudospectrum is actually a curve like this, but we cannot prove that. And it's not written in the theorem, but what we mean by there exists a constant m, that constant m depends on alpha. Yeah. So maybe I should have written independent of epsilon, but dependent on alpha. So this is what we know about the pseudospectrum of my operator. Yeah. How do we prove this theorem A? So let me just give you a sketch proof of that statement. So 3 steps. Step number 1, what we do is, because we have explicitly the kernel, we sweat and tears again, find the coefficients of the asymptotic expansion in Z up to order -4 for the real part of Z. Yeah, and take what happened in the asymptotic regime as real Z goes to plus minus infinity. Yeah. Secondly, so once we have that, once we have the norm of the kernel as a 2x2 matrix, we identify the leading order happens to be the indices corresponding to these 10 matrices, so 6 indices, as you see in the screen, 1, 3, 4, and so on. This drives the leading order of the norm of this. And then what we use for an upper bound on the resolvent norm is the Schur test. So this is a bound. So we prove the following statement as in the bottom of the slide. Yeah, the resolvent norm in a regime inside the instability band, yeah, imaginary less than 1, in a regime for which the real part in modulus goes to infinity, has a bound, essentially real part of Z squared for fixed imaginary part. And we know that the leading order is a constant. That is the same for the upper bound, yeah, and we prove that with the Schur test. And then for the lower bound, we use a construction of the pseudomodes, yeah. So essentially the same, and it's quite similar to the construction of our singular wild sequences for proving the construction of the essential spectrum, yeah. So the same constant for upper and for lower bound. So essentially we prove that in order to get the resolvent norm. In concrete terms, this is the result that we produce in the paper, yeah. So we have an upper bound with the constant now. So we know more. We know more or less how explicit they are in terms of the asymptotic expansion of real Z. Let me call the real part of Z tau here. So they are of this form. The upper bound in red, which we construct by the Schur test, we were able to calculate up to order -4, and the coefficient of the upper bound happens to be this term in red here. Yeah, it depends on the mass, it depends on the delta being the imaginary part of Z. And the lower bound we construct in a completely different manner. This is Schur test, and this is just pseudomode construction. Yeah. So as it turns, for our pseudomode construction, the constant match exactly. Yeah. Sorry, let me say it more carefully. The constant almost match exactly. It depends on the imaginary part, but it has a plus-minus correction of the mass. Yeah. But that's not a problem for our estimate. And then what we don't know right now is whether these two match. They may, but it's not clear. I mean, there is no analyticity here of the bounds. We don't know whether we do have an infinite asymptotic expansion for the resolvent. No? Yeah. What we know, for example, is that the limits, as I'm writing them here, converge uniformly in the whole band. That means for any delta less than 1 is an open set, but that's okay. And then for the mass, we can take any compact set, essentially. So this is the result that we prove for producing these pictures that you saw previously and the estimates on the pseudospectrum. And this is more or less what we know for the case of no potential. So we know more or less a complete description of what the spectrum and pseudospectrum of this model look like. What happens if I add a potential? So part 2 of the talk. What happens if I have a V, and for V, I'm going to assume that is an L1 variable is real, but is a generic Hermitian 2x2 matrix. Yeah. So in the Schrödinger case, we normally call it long-range potential. Yeah. And I'm going to assume two hypotheses. I'm pointing at the mouse. H1 corresponds to normal 1 less than 1. H2, my potential is L1 and a little bit more. So it's LP for any P, for some P greater than 1. Okay, and for example, it could be a bounded. So these are two hypotheses ensure, for example, I'll tell you why. I'm not going to show you the details, but I'll tell you why. Ensure that the formal sum of my Lm plus the potential in the natural domain of the sum has a self-adjoint extension. And all that I'm going to report from now is this is about this self-adjoint extension. Spectrum, pseudospectrum, eigenvalues, discrete spectrum, bounds, and so on. Okay? So these are the two hypotheses on B. And I want to tell something about the spectrum of this this closed extension of L plus B. And so our first result concerns the essential spectra from 1 to 4 in the case of zero mass or all mass, all from 1 to 5 in the case of positive mass. What we know is that for either of these two hypotheses, the essential spectrum remains the same. We don't know what happened for E5 for the case of m equals 0. So, so it remains the same. So it's these 4 bands that we saw in the case of positive mass or just the 2 segments in the case of mass 0. And so what I'm going to do now is to show you more results about the other parts of the spectrum of this operator, and then we are going to see a sketch of the proof. I mean, what's the proof of these results? I'm going to show you after I tell you 2 more results. So the first result is about what happened with the point spectrum in the case of no mass. So and what we have is the description of E5 of the essential spectrum E5 is rather more sophisticated for no mass, and so here is a distinction. Here is what we know about L0 in the case of perturbation H1. The point spectrum is in the instability band, namely the point spectrum would be inside the spectrum. Remember, the spectrum for the case of m equals 0 is just the closed band. And then if I have the hypothesis H2, essentially is in a band with a little correction depending on the LP norm of V in a suitable power. Yeah. Whenever P is equals infinity, the power here, so the P corresponding to the condition on the potential, this turns out to be a constant 1. Yeah. So it's a bit sharper than the limit, taking the limit to infinity of this. So it's constant 1, the infinity norm of V. We can do an artificial proof with that case. So this is what we know about the point spectrum for no mass. And this is what we know about the pseudospectrum for the case of general, okay? Mass 0 or so m greater than or equal 0, essentially. So so let me write it like this. Let me say it like this. We know what is the level of triviality of the pseudospectrum for these perturbations in the following sense. Suppose I fix a box which covers the endpoints of the 4 segments that are part of the essential spectrum. Yeah. So this box covers these corners of these 4 segments, essential spectrum comprising the 4 segments. Then we can say what the pseudospectrum part of my operator is in the box and in a neighborhood of these instability bands with an error. Essentially, the pseudospectrum would be in a band, which is correction epsilon, and then correction epsilon times the L1 norm of V. And this is the case where I can control the L1 norm of the potential by a constant. So I'm saying there exists a constant less than 1, such that if I control the L1 of V by that constant, then the pseudospectrum lies in essentially at the band with an epsilon correction, and the constant depends linearly in terms of the L1 norm of the V. And this happens including the case epsilon equal to 0. So I'm saying something about the spectrum in the general case. I'm saying something about the point spectrum of L, M, V for any M here. Yeah. So rather than writing it separately, I'm writing the statement for the discrete spectrum together here. This is what we know about the discrete spectrum, and the result collapses to this one in the case of no mass. Yeah. And what we can relate for the point spectrum and the pseudospectrum is that we can take the constant equal to 1 whenever there is no mass here, and essentially this result would collapse to this result here. Okay, so all of these three theorems, how do we prove them? I mean, what's the technology behind for proving these statements? And what we use is a Birman-Schwinger type principle that was established by several authors, but we could get the point in the end from a paper of Gestesi, Latushkin, Mitrea, and Sichenko. They produced this paper around 2000, and then we noticed because there was an erratum published in 2020 of this paper, and this is, let me describe what the actual key result that we use for proving all of these theorems. Yeah. So it's a non-self-adjoint version of the classical and fantastic Birman-Schwinger principle, and concretely this can be formulated as follows. Suppose I have that I have my potential V, and suppose I express V in polar coordinates. Remember this is a 2x2 matrix. The polar form of the coordinate the polar form of the matrix is unitary plus the positive part, and suppose I write B as B times A, and I take unitary half of the positive part in modulus for the B and the other half power for the A. I express my potential as a product of these two matrices. Let me set I call it the Birman-Schwinger operator. I do not know if this is the right terminology, but it's convenient for referring to the following operator pencil. Suppose we consider the resolvent of the unperturbed Lm, so that's R0, depending on Z. I multiply on the left by the A and on the right by the B, and I consider the closure of this operator. I can do that for any Z in the resolvent Z of the unperturbed. As it turns, and this is the key point of the principle here, if we can prove there exists a point in the resolvent such that -1 is in the resolvent of this Birman-Schwinger operator, then we note that there exists an extension of Lm plus V which has non-empty resolvent set. And moreover, we have an expression of the perturbed resolvent Rv, this is the resolvent of this operator, in terms of the unperturbed resolvent and the corresponding Birman-Schwinger operator like this. So for the proof of these theorems B all the way to D, what we do is we analyze this object here. We analyze the norm because we have an exact expression for the kernel of R0, and both B and A operators are just multiplication. Yeah, V is a potential. And we can write pretty much explicitly identity plus Q of Z. Yeah. So what we use is essentially the fact that we know everything about the kernel of the unperturbed operator. And that via perturbation arguments tell us something about the resolvent of this operator. And for example, if we want to fit the spectrum, what we use is these kind of things. Yeah, we analyze whether there are conditions, for example, for this to be of norm less than 1. And then that tells me something about the spectrum, because I know that this is a well-defined operator given this. Right? So this is the technology that we use for the proof of these results. And I'm getting closer to the end of the talk. So let me recap what we know so far about the potential case, and let me tell you about two more results that we have, and conclusion. So let me show you the cartoon picture so far. We have the instability band in pink on the screen. This is minus M and M, and we have the spectrum for the case of positive mass, which is just these two segments. And then if I add a potential, we may have eigenvalues, right? Depending on conditions, the eigenvalues would only be inside the band. Depending on conditions, there might be eigenvalues in a rectangle in a neighborhood of the origin. What happens if I do the following experiments? These kind of experiments are common in the case of the Schrödinger operators. Suppose I take the norm of my resolvent to 0. What happens with the eigenvalues? How do they escape to infinity? If the norm of the V becomes small, then we know that the eigenvalues are going to be trapped in the instability region, and they may accumulate in the essential spectrum essentially everywhere. For example, in the case of the model by Nguyen, Laptev, and Krejќi'r, they accumulate at the endpoints of the essential spectrum of Dirac. In that case, it's just one band, and they accumulate around this point. So what happened for this model? And the two next results are about that. We are imposing further conditions of regularity and decay for the potential here. And this is what we know given these conditions, case positive mass. We know that there exists a constant such that if I can if I have a bound on the L1 norm in terms of D, and this is a measure nu1 root of 1 plus x squared. So I am imposing an extra decay at infinity for the potential. Then we know that the point spectrum of LMB is inside the instability band, and actually it escapes to infinity. So essentially what I'm saying is that it should be away from the axis, from the imaginary axis, proportional to norm L1 of v to the minus a half. So this is a weighted norm just for condition on the potential, but this is the standard L1 norm. And given this, there is a natural question, which is the next theorem and the last theorem of this talk. So suppose we have then our potential fixed, and then we multiply by a coupling constant. So this normally we sometimes call this the weakly coupled model. So what happens if I have a fixed potential multiplied by coupling constant and take the coupling constant to 0? How is it that the spectrum, the discrete spectrum, escape through these channels, through these instability channels? And this is what we can prove if our potential is a little bit more regular. So suppose we have a potential in L1 with a decay now 1 plus x squared. And suppose it's regular in that it's in the sublab space of 2 degrees of regularity L1, W21, yeah, second index for the LP, the P in the LP. Well, what we know is that as epsilon goes to 0, the spectrum escape, the discrete spectrum escapes through this channel proportional to 1 over epsilon. So the previous result tells me that if I don't have restrictions on V and it's less regular, it would be 1 over epsilon to the half. But as it turns, if we want to be sharper, we know that the actual rate is epsilon to the 1. Yeah. So this is in complete contrast to the result that Nguyen, Leptev, and Tretter prove for the case of Dirac. So what happened is that when we open this channel, rather than the spectrum accumulating at the endpoint of the essential, it's just escaping to plus minus infinity. Okay, so that's the last theorem I wanted to show you. And then the closing remarks are, well, in case somebody asked, the answer is yes. What do I mean by that? So the question is, so we do have an example of a non-zero potential which has an infinite set of eigenvalues. Yeah. So it's not that the potential cannot create eigenvalues. And so if you want, this is perhaps the take home message of this presentation. And so all this analysis, all this, why? So it involves a lot of technical effort. It was about 3 years of our time. Why to bother about this? And to me, the motivation is the following. Non-self-adjoint operator matrices are different from the scalar counterparts. And these locations give a balance between something unusual and structure. So they can serve as benchmark models for understanding what is the structure of matrix operators. And this, to me, is worth exploring. Our manuscript is this one. We just lifted last month to the archive. And thank you for your attention. Thank you very much.
Thank you very much, Lyonell.
Thanks, Alexander.
We have time for questions now. So please, if you have a question, just write it in the chat or unmute yourself and we will relay the question.
Okay.
Alexander, I have a question.
Yes, go ahead.
Yes. For the case of the Schrödinger operator with complex potential, there are results by Weidel, Frank, Safronov, and Laptev in various constellations, which somehow, in some cases, estimate the Liptiering inequality quantity. So it's the sum of powers of eigenvalues. In your case, there one can expect the eigenvalues which converge to these 2 points plus minus m, and if one considers only those, is there a hope to get some estimates of this kind for the Dirac?
Yes, thanks. Yes, so I am rather familiar with these fantastic results, and I do not know what happened. It's a very pertinent question, and right now I do not know, but it's a very nice question about this about Dirac operators. Indeed, no idea is my answer. Yes, unfortunately.
Thanks.
But it's a beautiful question, and yeah, so it's something that we may consider, but it's yeah. I don't know.
Thank you. Are there any other questions or comments? Yes, Mark.
Lyonell, could you show us theorem C again, please?
Let me do it like this. Window, share again, and theorem C. Yes.
So here, so the hypothesis H1 is what, that the L1 norm of V is how big? Less than 1, was it?
Yes.
Okay. So basically what you're saying is that if you take your funny dislocated operator and you add a potential V, but V has to be real valued, does it?
No.
Okay, so
V is a non-Hermitian matrix.
Right, so you could add a dissipative barrier, right?
Yes.
But as long as its L1 norm is less than 1, you won't manage to poke any eigenvalues out of the essential spectrum.
Absolutely correct. Yes. Exactly. So this is weird. Let me explain what's my interpretation. The self-adjoint Dirac part is dominating, so that it prevents the potential, the V, to push the eigenvalues beyond the spectrum of the full thing. That's my explanation. And suppose you have just step as the potential. You can consider the dislocated part as part of the step. Well, at that point, the spectrum the potential is not strong enough for the spectrum to show beyond the band that is created for the L0.
I mean, there's no possibility, is there, of an eigenvalue from the lower half plane? Sorry, for a point, let's say on mz equals -1, to be pushed up above mz equals -1, still in the band, but be well, I guess there is, right? There's nothing to stop that happening according to theorem.
It could be an embedded eigenvalue, yeah.
And what about the spec E5 when you've got zero potential and zero mass? What do the eigenfunctions look like? Are they boring or are they special?
Spec E5, sorry. Okay, spec E5, let me go up a bit. In the proof of spec E5, the wild sequences that we use are a cutoff of the Dirac ones.
Yes.
My assessment on whether they are exciting or not, they are boring. Yeah, they are just oscillatories with this. It's just that you tune in the two components to create the band places. Yeah.
I see.
So yeah. So
okay.
I don't know if this is answering your question, but it's telling us something about the no potential eigenfunctions. Yeah. Yeah. So they should be kind of these oscillatory things. Yeah. Sorry, theorem C. Thank you.
Thank you. Anything else, Marco?
No, I'm good, thanks.
Thank you. Anyone else wants to comment or ask something to Lyonell? If not, thank you again, Lyonell, for this nice talk. And
Thank you.
we hopefully will reconvene next week. We are waiting to have some answer to decide who will speak next week. So meanwhile, have a great week and see you around. Thank you.